Dr. Oi Lam from Chinese University in Hong Kong, the Chinese University of Hong Kong, right? And she's an assistant professor there in the Department of Curriculum and Instruction. And she actually did her PhD at the Simon-Fraser University, Canada. And she has. We also have her in our MSc in Mathematics Education Study Board. She's serving as an external member. Now, this is the first of guest lectures that we are organizing through the MSc in Mathematics Education, offered at the Department of Mathematics, University of Colombo. So now in today's talk, Dr. Oi Lam will talk about technology-rich mathematics pedagogies, theory and implications, and so we can expect to hear how we can use technology. So all the new the research findings and all that. So without further ado, let me invite Dr. Oi Lam to deliver her speech talk. Over to you.
Thank you, Professor Geogebra Desmos. So it's great to be here, although we are in a virtual situation, but I'm very happy to and honored to do this talk. This topic, introduction to technology-rich mathematics pedagogy, is a passion to me, and I'm very happy to share with you some of my research interests and findings, and also have a conversation with you hopefully later on when the COVID situation or when travel restrictions are lifted. I hope to visit the University of Colombo to have more conversation with you on these topics. So I'll get started with my talk. Let's see if there's any, maybe it's this one. Right. Okay, I'll quickly do an introduction about myself. We only have an hour, so I'll try to be quick with these introductions, but I thought it would be nice to share with you a little bit of my history. But I have also used a timeline of the iPad evolution. The first iPad was created in 2010, and I actually started teaching secondary school before the iPad was born, so in 2005. So I started as a secondary school, high school teacher. I taught with many different tools. Some of them are digital tools, including the iPad. I've always been interested in using technologies to enhance teaching and learning. I started teaching AP Calculus, or it stands for Advanced Placement Calculus. It's a standardized curriculum in the world, but mainly in the United States. And it intrigued me to do some research in calculus teaching and learning, especially using digital tools. And I'll talk a little bit more about the tool that I will talk that I was using. It was called Dynamic Geometry Environment, and it's very good. It's an eye-opener for me, but also I find that this tool is very powerful, and I will be sharing with you more today. So that was a little bit closer to current, and that experience actually helped me did my PhD study. I did my PhD study with China Kia actually, and we met during our PhD study. So we had a very good exchange, and also I myself learned a lot more about technology enhanced learning. And then I moved to CUHK here in Hong Kong to take up my current position. And finally, just recently, I was a plenary panel speaker at one of the largest international conference in mathematics education. So just a little bit of background about myself, and also some interesting iPad developments getting bigger and bigger, as you can see. So in the beginning, I would like to have everyone to think about what transformation means. I think one of the key theme in this talk would be transformation, like transforming teaching and learning. But before we can talk about that, we need to know what this transformation means. And I'll show a couple of several images of technology here. I think that's it. So out of these tools, I think most of us here may have teaching experience. Can the audience do chat? If you are able to chat, do a chat, type in the chat. You can tell me like which tool is most transformative in your experience. There's 3D printing. There's Desmos, Geogebra. There's the Scratch at the bottom. It's a programming tool, and there's of course iPad and Kahoot is another tool. I'm not sure if you have used any of these or some of these before, but what I will talk about mainly is this type of tool and this type of tool today. In fact, I have also done research on programming, how we can integrate mathematics with programming, but I think today's talk, I won't have time to go into it. So I would say that the reason why I want to do some research on these two tools is I think they are very transformative. And I will define what transformative means to me in my next slide. So what it's important to know to talk about transformation, as I said, and I want to make sure that we are on the same page about what it means. So first, I would like to talk about what it does not mean, what it's not. And that's a very important thing. Like I think practicing teachers may think transformation is the same as, oh, it's very useful. But what does useful mean? And I think there's a distinction between transformation and efficiency. Efficiency means productivity, like how easy you can use it and how productive, how efficient something can be. Maybe it speeds up the process, but it doesn't mean transforming. It doesn't mean transformation. Transforming means something else. And so this is the first aspect I want to talk about. It is that it's not the same as efficiency. Although I think many practicing teachers are interested in being efficient, but it doesn't. Using technology doesn't have to mean that, or it can be efficient, but it can also be transformative at the same time. So there are two different things. Next. It doesn't always translate to better exam score. Once you use a certain technology, a tool, it doesn't mean that students will automatically improve their test scores. Why? Because I think that we are still stuck in a environment where the tests are being done in a paper pencil format. Students are still trying to write down their answers and do questions with this paper and pencil tool. And so there's still a mismatch, or there's some difficulty if you are using, there's some challenges when you teach students with technology, but at the same time, you test them without technology. As, for example, I think in Hong Kong, for example, we have a part of the exam where students are not allowed to use calculators. So that is already like something to think about. Like we may let students use calculators in some things, but we don't let them do it in a test. So there are some mismatches, and that's why I think that it doesn't always mean better exam scores. And sometimes I can also say that that better exam score can relate better to procedural understanding, whereas the kind of work that I'm doing, I'm trying to promote conceptual understanding using technology. So that's why there's a difference as well. Next, I also want to make a distinction between technology-rich and technology-enhanced learning. Technology-rich means you're using technology to promote mathematics learning, but sometimes people want to use this term, technology-enhanced math learning, taken for granted way. So they think that technology always enhances learning, but I don't think so. I don't agree with that technology always enhances learning. It really depends on how you use it, what kind of tools you use. So there's a distinction between those as well. So finally, what I think it is, I use an example of transformation in the mathematics sense. So mathematics, we talk about y equals x squared and y equals x squared plus 2. That's a transformation, at least in the English language. So we're transforming a graph or a function. And so therefore, I think I can say that transformation becomes a property change, right? We're changing the property of a function, or in this case, we're changing the property of teaching and learning. And what kinds of properties? I have laid out them here. So with a traditional way of teaching and learning, with paper and pencil dominant, we are teaching it in a linear way, an abstract way, given the paper and pencil tool. But with different tools, with digital tools, for example, we can actually transform these types of learning to teaching and learning to multimodal, hands-on, and technological. So, so that's the transformation that I'm talking about. Not necessarily better exam score, but really how students learn and how we teach. Of course, they're definitely hand in hand. And not only how, and also, as I would say a little bit more later, what mathematics is learned. So yeah, you may think that mathematics is always, it doesn't change, but actually, when one of the theories that I will present is that when you use different tools to learn mathematics, the mathematical concept also changes, so that the what also changes. So that's interesting, and I always go by this this statement that this is one of my significant statement to me in my research is digital technology transforming what and how mathematics is learned. And here's an example about what we can do with paper and pencil. So with paper and pencil, if you notice, I just copy somebody's math notebooks, of course. These are all identities, trig identities. They're called what, adding and addition and subtraction identities, I think. And in paper and pencil way, you just pretty much just write them down. And when you teach it, a lot of teachers just teach it by just telling them, the students, what they are. And I've seen this being taught by one of my students. They are, of course, undergrad students. They're learning to be teachers, and they just teach it like that. But in fact, with digital tools, so I'm talking about the transformation, right? So with digital tools, because I have observed that lesson myself, I'm gonna share this screen now. Because I've observed that lesson by my student, I realized that there's other ways to teach that concept where we can actually transform the teaching and learning. So first of all, of course, we can make it a very dynamic environment where alpha represent the angle, sine alpha, and cos alpha represent these two specific quantities or measurement. Respectively in this unit circle. And then for the addition and subtraction, say I take sine of 180 minus alpha, we can easily see that 180 degrees or pi radian, of course, is a half a circle. And then we can subtract alpha, and that creates this symmetrical, image. And then we can then see that sine of 180 minus alpha is actually equal to sine of alpha. So there's a visual way, and like I said in my slide before, it becomes multimodal. It becomes that the students can learn that identity in a visual way. This is at least one mode, additional mode to the paper, to the symbolic mode of learning, but also that the students are actually dragging this point. They're dragging this point and observing, and they're seeing different colors changing, of course. And this is also like there's a hands-on way of learning as well. And I also has said that before. So I won't go into much detail about this, but of course, we can explain all kinds of trig identities with this kind of dynamic diagrams. And the more interesting thing would be the 90 minus, right? And then you'll see that it actually is a I wouldn't explain. I wouldn't take the time to explain it, but 90 subtracting that would become two congruent triangles, but oriented in a different way, and therefore the trig identity can be expressed in the way that it is. So I won't go into details. I think we all have an idea around that already. So let me come back. And so here's an introduction, and I wanted to go back in time to talk about different tools in math. I think it's an interesting discussion as well, thinking about the tools that we're using currently, but also what have we been using before. So if we go back to ancient Greek, we've been using counting with fingers and the abacus. Later on, classical Greek, geometric, the geometry becomes more advanced, and there becomes more and more writing. And for example, in sans, becomes there's some tools being used here. Later on, there's the Arabic numbers. So this is the scripting. It's scripting. So writing down something becomes important, and we have been using that like many from currently as well. So for many centuries or thousands of years. And then, like we just saw, the numbers become symbols, and there's now algebraic expressions that can be written. And finally, in the 1950s AD, there's calculators being born, and more digital devices. So what my point is that if you think about the current tools that are being used in school mathematics, I would like to invite you to think about it. We don't have time to sort of have a discussion, but do we use any of these or all of these in school mathematics? So I actually draw on Natalie Sinclair, also from a Canadian scholar. She has written a very interesting statement, and I really like it. She said that we are currently using the 14,000 AD technology, which is this one, in an era where practitioners, so mathematicians, are already using digital technologies, demolishing the pre-Greek. Demolishing means we're not allowing our children to use our fingers to count, like we're demolishing this use, and finally delaying these classical Greek technology. So there's a confusion going on. I think like our use of tools are a combination of what we have been using before, but also we are not allowing people to use, or our children or our students to use fingers because it seemed like it seemed elementary or something. But as we said, as I would say in my presentation, I will challenge this notion of not letting our students use fingers to count and to do math. So this is just some interesting discussion there. As far as tools in the current days or in the digital era, I think that one of the I would like to talk again is somewhat of my assumption. What tools can do for us. It's not only teaching and learning. I've talked about teaching and learning a lot, but I wanted to also stress that tools can support mathematical thinking. And so what does thinking mean as opposed to learning and I guess learning? So what are the differences in here? And I think as math educators and myself as a researcher, I think it's important to know the difference between thinking and learning. For thinking, it's more about cognition. So here it is. I will use an example to talk about it later on. For thinking, it's like engaging in mathematical idea. So in here, let me actually go to this, again, transformation, but it's just a pun. So here are some points, and I would like to use this as an example of talking about mathematical thinking and learning. So here, I'm gonna drag these points and you can tell me what happens. It would be more fun if you to drag it yourself, of course, but I'm dragging this and I'm trying to drag this, but this point E does not move. So I'm actually learning something here, is that this is not a independent variable. I cannot change it, but perhaps I can change other things to make that change. Let me try dragging A, and it does. So if I drag A, I will notice that E is moving in a certain way. And I'm sure you're thinking of something already. And if I were teaching this using this tool, I would ask my students to specifically describe how is E changing in relation to A. My hope is that the student can talk about E as changing at a constant, it's moving in the same way as A. It maintains the vertical and horizontal distance from A. So there's these concepts that are being brought forward, and the student then is actually doing some mathematical thinking. If I'm dragging this A and the student is describing how E is moving, that is already engaging in some mathematical thinking. So let me try and drag something else. What will happen here? And again, I will try and ask my students to talk about what is going on here. For example, what's going on here, and also what's going on here and here. You see, like something like this. I'm not being able to like this. So if I drag it horizontally, what will happen? So the students are engaging in mathematical ideas, and that's what I call mathematical thinking. And let's do one more. Oh, I can't drag this. Let's try to drag L then. So this is a different way of, or it's not really different, but it was slightly different. And then now we can see that there's a little symmetry line here, but the line of symmetry is not, it's just a formalized term. So it's not important for mathematical thinking. So I'm just using this example to show what I mean by mathematical thinking. So it's engaging in mathematical ideas. So when one learns mathematics, there's a change in the way they talk about mathematics. So at the end, we can tell the students that this is actually called translation. This is called reflection. And so students are able to pick up these new terms, and they can now change the way they talk about it. They can use these new terms and say, oh, this is a translation, this is a reflection. So there's a change in that way. Finally, teaching is, of course, occasioning opportunities for students to think and learn. So that's my type of, my philosophy or something that I really believe in. And so the fundamental ideas for me in my research is how can technology and tools afford that paper and pencil cannot, right? So if our tools, the tools that we can try and use can afford something more than about mathematical thinking than paper and pencil, then we are really, as teachers, really happy. We can provide more learning opportunities for students to think, to engage in mathematical ideas in a deeper way. So we're starting to think. Our starting point should be mathematical thinking. How can tools help our students engage in mathematical thinking? And from there, we will design our pedagogy. So my point here is that we don't do it in the other way around. We actually think about how thinking occurs with the use of tools, and then we try to design ways to help our students to occasion that thinking and learning. So and whereas it's not this way, we're not going to design pedagogy and without thinking that how it's going to happen and so on. So that's something to talk about. I think I've already use up a lot of time, but I think these are some of the fundamental ideas I use. So I want to quickly talk about two types of technology. Before that, I'll show you some research papers, and please notice what are in common among these papers. Okay, so almost there. So in fact, if you have noticed, all of these papers talk about gestures, right? So so why is gestures related to math, right? And so in this section that I'm gonna talk about, I would like to really talk about a theory, and then from there the implications on thinking and learning, and then implications on teaching as well. So what about gestures? So let me move on. Gestures and thinking. Another practice that I usually tell my colleagues to do is try and explain sign law to a colleague by sitting on your hands. So you're not allowed to use your hands to talk about sign law or any kind of geometry, some kind of properties. So if you really practice this, try this yourself, you may find it difficult because you're not allowed to use your hands to talk about some angles or some triangles and so on. That's some experience for you to try and then think about. Also try to do this also sitting with your hands, like some very difficult long multiplication. The reason why it may be difficult without doing without your hands by sitting on your hands is because sometimes you kind of try to use your fingers to kind of locate the numbers while doing the long divisions, long multiplication. Sorry. So there's something going on in our hands when we think. So this is my slide on gestures and thinking, right? Let's move on. Evidence that your hands are doing the thinking. It's not that your hands are helping you doing thinking, but that your hands are actually thinking. So let's find some research evidence there. We know we have research showing that gestures, when gestures are used, students do better on spatial reasoning. So here's an example that when gestures are encouraged, they make fewer mistakes. This is an error rate, right? So it's not a performance rate. This is actually they make fewer mistakes than when gestures are not allowed. Prohibited. Sorry, they must not be used. Okay, so there's a difference there, and so research shows that when you use your hands, your spatial sense becomes better, and that's why I use this sign law example. Like it's a geometric example. Next, not only geometry, but in fact, when students do arithmetic, very young children, right? You will see that, or actually not young children, anybody, like it's regardless of age. When you doing some arithmetic, your brain actually activates, the part that sees fingers actually activates. Even if you're not really using your finger, but when you're calculating something, you're doing arithmetic, the part that sees finger actually activates. And there are also some studies which talk about achievement, so I won't talk about that now. And finally, gestures can contribute to better communication. Of course, while I'm talking, I might be using some kind of gestures to deliver my message, so I'm communicating. It helps me communicate, but at the same time, it doesn't really only help the listener, but it actually can help myself, the speaker, because how many times have we talked on the phone, but we're still doing this kind of gesture? We're using the phone, so no one is seeing us gesturing, but we're still using gesture enough when I'm talking about the phone. So it helps the speaker to also communicate as well. So these are some of the interesting facts about gestures, and also related to math as well, math thinking and learning as well. So implications for teaching and learning. like I said just a few slides ago, my take on this is that we should promote gesture. We should not let our stop our students from using fingers to count, to do any kind of math. We should definitely not let them sit on their hands, of course, and so on. So, and also teachers can actually model gestures use as in here. These are taken from different studies. And so these are the roles that, as a teacher, you can actually model some of these gestures to help to communicate the mathematical idea, and also to help the students think in that way, and also they can create those gestures themselves to help them learn. So another implication, I think I should go to a theory behind this really quickly. I won't go into in detail about that. Is that the theory behind something about gestures and thinking is called the embodied cognition. Embodied cognition is theory where it argues that cognition is shaped by our motor system, the perceptual system, and the body's interaction with the environment. So the body's role is very important in cognition. And that's why not only your hands, but of course, any part of your body can actually contribute to cognition. Embodiment of the mind means that the detailed nature of our bodies, our brains, and our everyday functioning in the world structures human concepts and structure reason. So, so a lot of people think that, oh, thinking happens in the brain only, but in this theory says not. It doesn't only happen here, but it happens everywhere in your body. Like, so that's why I said your hands are thinking, not only your brain is thinking, and so on. So that's why it's an interesting theory to think about as a teacher. And also there's, because of the bodily experience, when you learn math, you may actually draw on different metaphors. And we have also used this in our teaching. I mean, it's very common to think of functions as machines, what else, sets as containers, and so on. So that's the basis of this theory, is that because we experience these in everyday life, it's easier for us to learn concepts in math by drawing on our own experience. So the metaphorical thought is a very important mechanism or process for learning. So I won't talk about this, and I won't talk about this either. Let me go to my next slide. So these are some more examples about metaphors, but that's not really my point. So, okay, so back to embodiment, embodied cognition. So here's an example and a tool. I will show you a video of touch count. Touch count is an iPad app where anyone can use their finger to see numbers. Not only see, but they can actually, as you see here, they can tap, touch, see, hear, and make numbers. I think this is actually missing the sound. When you gesture by putting 5 fingers on the iPad, there's a sound of 5 in there, and there's a number 5 and 5 circles. So there's a multimodal aspects of numbers going on. And this is another version, or a more advanced version, where you can do multiplication, because you can do, in this case, 2 sets of 5. And here students are actually using their gesture, their fingers, to think about multiplication, having how many sets and how many in each group. So back to the idea of embodied cognition, we're trying to make use of in this tool, students' hands-on experience, their gestures, to help them think about math. And of course, they are very engaged in it. This is a research taken from Canada by Dr. Natalie Sinclair. And this app is actually available for free download. So in the App Store. So for elementary students, elementary school teachers, it would be very interesting to try that out. What else? Let's see. So going back to the key term of transformation. So using this tool, let's talk about how mathematics or what mathematics is learned first. Here is what mathematics is learned. We are actually letting students learn one-to-one correspondence through the tapping. So one tap is one thing, and they can sense that, they can experience, feel it very strongly, right? The ordinality is that they can tap and it says one, they can tap again, it's two. So there's an order of things. For cardinality, it was that they put 5 fingers at once, and that stands for 5 items. So it's how many in a set. And also number as symbols. So at the end, as I said, there's a multiple representation going on, very strong there. You can hear the number being called, you can see it, you can count it yourself, you can see the symbol. So so very helpful to connect those representations. As far as transforming how it is learned, and I've already talked about this, tactile, visual, and auditory feedback. It improved finger perception, which is what we were just saying in the research finding. One of the research findings is, I think I didn't mention that one, but people with better finger perception, they actually do score better in math in grade 1s and 2s. So better movement with your fingers actually help with math learning. But this is an elementary school level, or actually even kindergarten level. I'll go into another tool, and also some other school level to have a variety of examples. So in my next tool, I'm not only talking about gesturing, but I'm talking about making as well. So gesturing, making, and thinking. Here's a video. I hope you can see it. If not, please let me know. So this is another research of mine where I have been interested in using what's called the 3D pen. This is a 3D pen because when you draw, you can actually draw in 3D. So this is a very interesting tool. I've started to research about it a few years ago. And of course, one of the affordances, right? Something that you can do, but paper and pencil cannot, is certainly to draw in 3D. So back to the question of what can you do with this tool, but not with paper and pencil. We know that for young children, when they struggle to draw 3D solids, to 3D shapes on paper and pencil, because it's a 2D environment, right? So it's really just a 2D representation. So they have problems with this, but in my research, children have no problems drawing it in 3D because of the tool they're using. So the tool really changes the way we learn. Next. Here's another video to share with you. This is a more calculus topic where you're talking about cross sections to calculate the volume of this solid with cross sections that are squares and a base that is a circle. It's much more helpful if the students can actually visualize what it looks like. And a lot of times when we do calculus problems, calculating the volume of something, they don't even know what it looks like, and they're just sort of memorizing procedures. But if we actually help them visualize the cross section, it would be much better. So of course, this is a way of helping students visualize in the calculus level. Next. Here's one of my favorite videos. What it's showing is that you have two axes, let's call it X, Y, and then you have a point on the XY plane. And I lift this up, and then with my left hand, I am rotating the axis, and I rotate and rotate, and until I rotate this axis 360 degrees, what will happen is it will create a circle. So here's a hands-on experience of making a circle in a very different way, not in a way like this, but actually by simply rotating the axis or spinning your axis or spinning it while the other point stays stationary. You just need to spin it, and then, of course, by spinning the point at a distance from the axis, you will get a circle. So very new modes of thinking about the circle, right? You're actually using your hands and using tool, interacting with it in a new way that paper and pencil cannot. So this is one of my favorite. And finally, when we talk about geometry, something even as simple as a triangle. Here you see me drawing a triangle, and it's 2D. But the nice thing about using a 3D pen is that you can lift it up, and it becomes a manipulative. And you can rotate it, you can flip it. And so the triangle that would have been drawn on paper and pencil, that would have been stuck on paper and pencil, it now becomes something that you can touch, you can manipulate with, and also like do some kinds of transformation with it, like I said, reflecting it and so on. So another new way of teaching and learning and teaching and learning and thinking with this tool. So that's why I have been interested in research around 3D pen. And so here's some examples in Hong Kong where students are using 3D pen to draw three-dimensional shapes, and they are the teachers helping them to generalize the number of faces in a triangular prism and rectangular prism and so on. The number of faces, bases, and lateral faces and so on. So here's an example. There's some inquiry-based learning here and generalization here. More snapshots of the same thing, but trying to show how it can transform thinking and learning in these ways. Promote deep learning, and then active learning and hands-on making. They're actively creating something while learning about properties of prisms and pyramids, of course, and they create something personal at the end. And this is one aspect where I really like, where students at the end of the day will tell you, I made something, rather than I learned something. So in math, we seldom help our students or teach our students how to make something. But in here, with the use of 3D pen, they can make things from nothing. So they're making it from raw materials. The making process actually is part of the learning process. Something else I did was that students can actually create cross sections. It's a very difficult topic in primary school here in Hong Kong. So I designed lessons with teachers where students would use the 3D pen to trace around a solid to visualize the cross section. So imagining there's a cut through a certain prism or solid, and imagine what the shape would be like. So you can see here two kinds of cuts of a cylinder can create either a rectangle and a circle, right? Of course, and even some can be ellipses, of course, if it was a slant cut. But students can actually explore these with the use of 3D pen. While they're exploring, they're actually also importantly using their hands to move around the objects. So there is the gestures that come into play, and also when they're making this in the other lesson as well, they are also always making the gestures and of like they're making parallel lines, and they're doing perpendicular to the base and so on. So they're already engaging in those mathematical or geometrical concepts with their hands. Here's just more examples. Some difficult examples would be the pyramid, where there's a cut perpendicular to the base, but the students do overcome, and they actually learned something that they did not expect before. So they would predict something, some shape before, drawing it, but now after using 3D pen, they actually changed their thinking. So we see that from some of our research. And the example with the secondary school would be the Euler formula. Students can actually draw different platonic solids and explore the formula there. I will try and skip through a little bit. Also, 3D trigonometry is a big topic in Hong Kong, and we implement some of these 3D printed objects with the use of 3D pen for students to see the angles between planes and between lines and so on. So this would have been a very difficult topic to teach if it was on paper and also like on 2D surface. Finally, some calculus examples here. So students are using graphs to feel this tangent to the curve feeling. They push a line, a straight line, and push it so that it just touches the curve, and they can actually feel like the tangent, the tangent idea in that way. And I think that's it. And the integral example as well. Here's a video showing again the revolution around an axis, but this time we're letting the student draw this 2D and then create the 3D, and they would be able to see and visualize what the actual 3D would look like. In so doing, they are actually supporting the visualization in embodied ways. So at the end, here's just a quick recap. I was talking about gesturing. I was talking about how gestures and thinking are not related, but they are the same process. They support one another, and basically, and then I went on to talk about this tool called the 3D pens. My research really talks about 3-dimension or 3 aspects of this tool. The first 2 aspects, of course, it allows us to have to create an artifact, so artifact construction. Next, there's some inquiry-based learning there, and there's not only that, but students are trying to do some engineering design. They're doing some STEM thinking there. Finally, new tools of thinking. The new tools for thinking, I mean, for example, which I have talked about in this throughout, is gestures. It's a tool for thinking. So the more we allow our students to use our hands, the better, actually. So that wraps up. I won't talk about it. That wraps up my first section, or one of the tools that I want to focus on today. Some recap about that tool, and I'll let I'll share the slides with you. So because I have a little bit more to share today, I will go into. I'll go into my next part where I talk about moving and thinking. So not only moving with your hands, but just movement in general. So here's a difference. Here's something on the left. You will see nothing is moving. It is a very typical example of a quadratic function. And even if there's a transformation going on, let's say from here to here, like there's but we see nothing being moved, right? But if we use a dynamic environment, something is moving, what will happen? So here's an example of a function, and I would like the audience to take a look. What is happening to f of a? You can't really see it right there. What's happening to f of a as I move a from left to right and from right to left? And what's going on here? So what is this function, do you think? Is it a linear function? Is it a quadratic function, and so on? So, but the key is that like with a different tool, we're talking about functions in very, very different ways. Look at this. Whoa. Very interesting, huh? So it never, this function or this g of b never becomes negative, right? That's one thing. And this change is very interesting too. It's very fast, you can call it. So because something is moving, you can talk about it in very different ways. And so this part of my talk will be about, thinking about math dynamically. Oh, wow, here, look at this. Nothing happening, but something happening there. So you can think about what kind of function does these represent. And finally, one more very interesting one. What is this one all about? Okay, but this one, I know what it is, so I'll share with you. This is a step function, right? So step function, but in a step function, really, if you do it on a XY plane, Cartesian plane, nothing really moves. So again, I'm trying to talk about how movement actually changes thinking, right? Or changes the way we're attending to things. And here I would like to use a quote from René Descartes. So this is who is also the very person who created the Cartesian plane. So René Descartes says, "I think, therefore I am." So what he thinks is important is really him thinking is the most important thing. So he doesn't really emphasize movement at all. He thinks that staticness is important. He actually tries to create this XY plane to undo all the motions or undo all the movements, as opposed to movement that can be seen in our functions. So another movement that I would like to talk about is this type of movement. What's going on here is that we can see some relationship between the point C and what it's drawing, and there's something around, of course, the number pi there, and what will happen is at the end, it will actually make a very beautiful shape. I will let everyone try it. I will share my slides. If you click on this link, and you will actually find a very beautiful shape. So my point here is that in thinking about Descartes, we can actually change what he says, that I think, therefore I am, by the word I move, therefore I am. So move is actually very very fundamental to our experiences. Like we actually move all the time, and whereas when we do math, it's more static than real life. So I think what I want to argue or encourage is to put movement in your math teaching and learning activities. And how do we do that? Is of course use tools to do that. I will share with you what I have been doing. By the way, the word motion and emotion, very interestingly, emotion, there's only like one E difference between motion and emotion. So movement actually brings about emotion, and I think it's a very true statement anyway. So let me go to some important research on dynamic geometry environment. So dynamic geometry environment are something similar to, or one kind of it is the Geogebra. I think some of you may know. There's Desmos, there's Geometry Sketchpad. Those are representation of math relationships in a dynamic way. So I have gathered some of the affordances of DGE in research I would like to share with you here. Oops. So on in this video, you will see that here's a triangle, and I'm moving the three vertices of the triangle. One more time. And it changes obviously the shape of the triangle, but this is a very important affordance about dynamic geometry environment is a way of thinking in a dynamic way, so that the triangle is now not only this shape, but it can be this shape. We know that in children have difficulties thinking that this is a triangle. They will, if you ask them, some children will say like they may say, no, this is not a triangle. But because of the dynamic environment where they're dragging and dragging, and they realize, they may realize by dragging that these vertices that as long as there's 3 points and 3 lines, then any shape can be a triangle. So there's this dynamic mode of thinking that is added to learning about triangles. And you, of course, at the same time have limitless examples of triangles in this case, and limited examples of any shapes in general and any functions, with different parameters, for example. So here's an affordance. Next, oops, I have just made a mistake there. Next, I will show this video. Here on the top right here, we're using DGE, this tool, to help us see a 3-dimensional object like the ones that I show with 3D pens, something that would have been hard to visualize. But here you can actually see different cross sections. You can even change the cross section shape very easily and imagine what it looks like. So what is the affordance here? It is supporting visualization. Next, show this video. Here's a triangle again, but this triangle is changing, is acting differently. So when I'm moving these vertices, something seems to be not changing. Something seems to be invariant, right? And you realize that this is always going to be an isosceles triangle. So it allows, or it invites in exploration of what is changing and what is not changing. And you can actually see relationships much better because of this dynamic situation where you're changing something, but something may stay constant. And this is why what I mean by mediating variance and invariance in a dynamic geometry environment. It's very easy to see what's changing and what's not changing, and it helps you explore mathematical concepts, but also to really help with the understanding what is the invariant property, for example. Lastly, here's an example. Here's a function, of course, and then we can drag points on this function and create or see a secant line. The secant line can then be drawn. One of the points can be drawn to infinitely close to each other and make it almost a tangent line. And this is an example of course, the calculus first principle definition of the derivative. So in a dynamic environment, this helps us, of course, see the functional relationship, the functional thinking that, here we have x and f of x, the relationship of these, because you can drag a point and see how f of x is changing according to the movement of x. And finally, multiple representation. What we just saw here is not only a graphical representation here, but also algebraic and numerical representation all in one on one screen. And so it really helps multiple representation. And finally, when something is being moved, and you really can see the others also changing. So there's some connection between multiple but between the representation as well, not only the multiple, but connections to those. Next, I think I'm running a little bit out of time, so I will go into this implications. So just to use up a few more minutes to wrap it up. So I was talking about dynamic geometry environments. As promised, I will talk about implications for teaching, right? So given that there's this like moving moving helps you like moving and thinking, right? The relationship there. What can we do in our teaching? So for me, I have made some suggestions for when you design dynamic geometry or use dynamic geometry, try to focus on some aspects. So we want student-centered dragging, student-centered dragging as opposed to teacher-centered dragging. So we want to allow students to do the dragging themselves. Hopefully they have their own device and then they can do the dragging to explore the, like I said, the to help them do the dynamic thinking. They can also see what's changing, what's not changing, much easier than if the student were seeing someone else do the dragging. So it's also important to by dragging themselves, they can realize what is draggable and how is it draggable. So those are important. Yeah, and here's an example locus, right? I can share with you these examples and later on. And locus is something where you in this case, the students needs to drag to satisfy a condition. And so this locus of points will satisfy the condition that it is equidistant from AB, and it becomes actually an angle bisector of, and so on. So students needs to do the dragging themselves. Otherwise, it would be really difficult for them to learn the concept. Okay, a few more. So one of my research findings says that, or suggests that we wanted, in this case, right, we've seen this example already before. We drag this point along this unit circle. So it's important for students to drag an actual mathematical object. So this is a mathematical object, is a point on the unit circle, as opposed to something like a slider. So I don't encourage the use of sliders, because a slider is another mediation of the meaning of the angle in this case, right? So if you can actually make it very directly, like the draggable object is actually has meaning, it carries mathematical meaning, it's much more easier. The hand movement and the dynamic movement is already it already pertains mathematical meaning. In this case, like we're dragging along the unit circle, much more meaningful dragging there. And there's another example is dragging the point. We have seen this also on the function, rather than using a slider again. So we can slide X around, but it's not as meaningful. And so I really emphasize that. Two more implications. Numbers as continuous. So in our dragging, also we want to try to make it a continuous dragging. So Desmos are very handy for that. You can easily create sliders, although these are sliders, but these are parameters for something like polynomial functions, let's say. So when you drag, you want to really let students drag continuously, not really discretely, because in cases like in polynomial function, for example, the parameters can be any number. So you don't want them to be dragging like 1, 2, 3 discretely, but really it's a continuous variable and so on. So they can understand more about what they're dragging. And so if you design something, try and make it more meaningful. The same for something around data. I guess in statistics unit, you can have students drag different points to show the mean, the plot, right? Mean, median, mode, how it's changing according to the data sets. It's a very, very powerful way of teaching statistics, actually. So I would suggest that, but running out of time, of course, but I can share some links to everyone. And finally, what I didn't really get to talk about the theory behind it, but I would encourage using less words in your DGE and also in your teaching, but let students focus on the visual signs. So if you really want them to engage in mathematical, to engage in your DGE, I think less words is better. So letting them really focus on the visual meaning, what can be conveyed there. Of course, if they don't really know how to use, then of course that would be difficult. But you can help them with using the tool, and then after they know how to learn how to use the tool, they can then really try to focus on what can be learned from the visual. I think that can help them internalize the meaning, but that's based on really the theory of semiotic mediation, which I don't have much time to talk about today. So I think that's pretty much all for my talk. So I will stop here. I think I've run out of time. Thank you very much for your participation, and I'm happy to take questions. Thank you very much.
Professor Lam, it was a very interesting talk. Thank you. And the audience can ask questions through the chat box. You can send your question to her, right, through the chat. Or maybe shall we ask them, whether they want to unmute and speak, whether they want to do that? We'll first try see if there are any questions to the chat. Okay, since let me ask you questions, right? So maybe the questions will come in, right? So now you said that you differentiated between technology rich and technology enhanced, and said that technology always doesn't enhance. What did you really mean by that?
Right. I would just caution that the belief that when you use technology, you will always enhance. It's just not always. I think the terminology technology enhanced learning implies that it always enhances, right? Because that's why it's being that's the way it's been used currently, and it's a popular term, but like I said, I was trying in my presentation to show that it's not just the technology itself, but actually it really is about the theory, and then the theory, how it informs thinking and learning, and then like how this tool can transform the thinking and learning. But of course, it also involves the educator as well. So it's not just the technology itself can do any enhancing. It's really a combination of many things. So it really needs the teacher. There's a theory behind it, like theory informed type of usage of the technology. I think though a combination of this can enhance learning, but not just the technology. Does that make sense? Because if I give you a 3D pen, like nobody like it doesn't guarantee that it will enhance learning. I think that's the kind of message that I want to share.
Okay, now there's a question in the chat box. Can you see it?
I can see.
If you can't see, I can read it. Can you see it?
I can only see the thank you one. Oh wait, direct message to me, right? Okay. Okay. One is about science. Is it that one? But now we understand the science behind how effective it is. Oh, okay. So, I see some messages that the audience is quite positive about the presentation. They think that they can really see how effective it is and the science behind it. There's there's an audience asked about where can they get the graph tools to learn calculus graphs. So I designed them to myself. So with these DGE environment, they are open. Some of them are open source. The two that I mentioned, I will share in chat again. Geogebra, if you just Google Geogebra and Desmos, those are the two graphing most popular DG where they're free to use, and you need to design your own environments, or you need to design your own screen, your own sketch. So I'm happy to share with you. I have a link right now. I should do it right now. I should share. And then this is just to give you an idea of what I have done throughout my career as a teacher, but also as a researcher. So there we go. Yes, here it is. So I'll share through chat. Sorry about that. So there are a collection here that I've designed myself. And let me come back to other questions. How effective would it be in Sri Lanka, a country where there are thousands of students with struggling family economic backgrounds and with underdeveloped IT exposure? That's a good question. I really appreciate it. I'm in a different context, and here in Hong Kong, there is a lot of resource for schools. There's almost always a class set of iPads for every school to use, and I understand that Sri Lanka may have different contexts, and I think it's really the educational I guess the government and the education department who needs to take up the resource responsibility. So I really think that it's out of the teacher's control right now if it was in this situation. And I totally agree that the resource can also be allocated to something more important like family economic, like you were talking about students who are struggling with family economic background. So I think it's not it may not be a priority right now, but I think eventually if there's resource that could be allocated, it can be allocated to schools. So thank you. Okay, there's a good question also. Romaine asked, when technology use, the what of the mathematics itself is different. What is the concepts are different? So why is that? Here I can share with you a slide that I skipped because yeah, I think that was really nice that you picked up on that. So I did talk about the what being changed, right? But here I did miss that one. So let me quickly show a slide if I may. Oops. Why are we back here? Yeah. So here's an example where to draw a circle, you can use different tools. So this slide will help me explain why what I mean by what mathematics is learned, like changing what mathematics is learned. And with this tool, of course, using a plate and a pencil, you can draw a circle in this way. And what kind of concept is being learned here? think about it. The audience can also think about it. What kind of concept is being learned is really the idea of curvature, right? That you're not really going off tangent here. You have to always turn, and the angle of turn or the kind of curvature you're making is always the same. Otherwise, if you don't do that, you cannot make a circle. So this curvature thing, right? Otherwise, you can make a spiral, of course. So there's this concept being learned or being engaged in with this tool, and then what about another tool? In this case, we're talking about like, is it a compass, I think? So with a compass, with this tool, when we draw a circle, what kind of concepts is being learned? It's quite different. It's actually the idea of the radius of R, right? That is constant. Whereas in this case, the radius of R is never really important in that tool. So here's two examples of different tools showing us different concepts. That's what I mean. I shouldn't say that the concept is changing. It's really just what concept is being learned is changing. And finally, one more tool, and this is again the dynamic environment, where I changed the number of sides of polygon from 4 to infinity, and I can also make a circle out of it. And this is actually the way how we estimate, or approximate pi by using the Archimedes method. But it's just another, in this case, is another example of how this tool is changing the way we learn. It's changing the concepts that are being learned with this tool. Along with this tool, we're talking about infinity. We're talking about limits. We're talking about geometry, more like geometry, like how we are starting with a polygon and then it becomes the circle. So I hope that explains your question of why I say that what mathematics is learned is being changed with different tools. You're welcome. Okay, let me just. There's one more question. Let me try. I want to clarify the question. So there's a question about, we address what is mathematics using technological tools, how we get technology into the question, why mathematics? Oh, I understand now. So I'm afraid I did not really, in my presentation, I have not really addressed that. So the audience here is interested in answering why mathematics, because his or her students are really interested in why. They want to ask the teacher why, I suppose, why they're learning mathematics. So I think, right, why mathematics means why do they need to learn mathematics? So, and how does technology, come into play? How can it support or help answer that question? Well, why mathematics? I think it has to do with students' motivation, right? If students ask such a question, it would mostly mean it might mean that they are not interested, they're not motivated to learn mathematics. And so they ask, why do they have to learn it or something, right? But if you use technology, it is something that they are familiar with. I always tell my students that like this, we're living in the 21st century, and everybody has digital, in Hong Kong, everybody really has digital devices. They are very in tune with technology, but it's like when they go to school, they're not allowed to use any technology. So it's like really kind of there is a problem. This problem is that like in school they're really out of touch with the technology that we're currently using. But so if we bring the technology into mathematics classrooms. Hopefully, to answer your question, the students can become more interested because they think that wow, they can actually use this to learn math, and they can see something dynamically changing, and it can, to me, in my experience, it really can help with students' interest, increasing their interest. So that's my answer to that. One other question: which age group are these tools most effective with? Which age group are these tools most effective with? I've given a range. I've given, as you see, the app called Touch Count, where you play with numbers with your fingers on an iPad. And then there's also dynamic geometry, 3D pen. That range I've worked with is like elementary school to secondary schools. So I wouldn't say most effective with. I think in response to what I just said, our students, at least in Hong Kong, they're really familiar with technology anyway. So like at a very young age, they have used screens, devices, so and then touch screen, of course. So I think they're getting more and more familiar with, and I would suggest that it can be any age range, but it has to be, of course, the task and the tool needs to be age appropriate to those group of students. Then it will be fine, I think. So I wouldn't say there's an age group that it's most effective with. I think that's it. So back to you, Chanakya.
Yeah, I think now it's 11:22. Maybe we can wind this up. So once again, thank you very much for a very interesting talk. And thank you everybody who came to this talk. And we'll see you again next week in the second talk. So thanks, Oi Lam. So we'll see you again.
Thank you. I hope to visit you when the travel is getting better. Travel.
Sure.
Okay.
We'll definitely arrange something for you to come and deliver here.
That's great. Okay, thank you very much again for your
Okay, thank you.
Thank you.
Bye everybody.
Bye-bye.